Earth formed 4.54 billion years ago, a molten sphere bombarded by asteroids, volcanically active, with no oxygen and no life. By around 3.8 billion years ago, Earth cooled enough for oceans to form. The first life, probably anaerobic microbes, evolved in these oceans. They thrived without oxygen, using methane, sulfur, and other primitive metabolic processes. Then, a major evolutionary breakthrough occurred. Around 2.7 billion years ago, a group of bacteria evolved the ability to capture sunlight using water and carbon dioxide, producing glucose and releasing oxygen. These were cyanobacteria, the first known organisms to perform oxygenic photosynthesis. This was a biochemical revolution. Oxygen was a waste product for them, but it had global consequences. For millions of years, the oxygen released reacted with dissolved iron in oceans, precipitating rust and forming banded iron formations, iron-rich geological layers that still exist today. Once iron was saturated, oxygen began to accumulate in the water and then the atmosphere, leading to the Great Oxygenation Event about 2.4 billion years ago. This oxygen buildup was catastrophic for existing anaerobic life, triggering one of the first major mass extinctions. But it also unlocked aerobic respiration, which produces about 18 times more ATP than anaerobic metabolism. This allowed evolution to move toward larger, more energy-demanding cells. However, oxygenation wasn't immediate or global. Deep oceans remained anoxic or even euxinic, rich in toxic hydrogen sulfide, for hundreds of millions of years. Cyanobacteria continued producing oxygen, but much of it was absorbed by minerals or trapped in shallow water. Meanwhile, they formed visible stromatolites, layered biofilms and sediments that dominated shallow marine environments. Some still exist in places like Shark Bay, Australia. Only around 800 to 600 million years ago, enough oxygen reached consistent levels in surface oceans to support multicellular eukaryotes. This led to the rise of the Ediacaran biota, the first complex macroscopic organisms. By the Cambrian period, around 541 million years ago, marine oxygen reached thresholds that allowed for higher metabolic rates, hard shells, movement, and predation. This triggered the Cambrian Explosion, a rapid diversification of animal life and body plans. That explosion, and every complex organism since, owes its origin to the silent oxygen buildup started by cyanobacteria over a billion years earlier. Even today, cyanobacteria are essential to life. They contribute over 20% of Earth's oxygen, fix nitrogen in ecosystems, and are studied in biotechnology for sustainable fuel, agriculture, and even potential life support systems in space missions. Without cyanobacteria, there would be no oxygen-rich atmosphere, no mitochondria, no animals, no humans.